In this video, I introduce positional information embedding for transformer. Transformer model doesn't contain all the information of an input sequence, since it takes one sequence as a single input, as shown here. This is input, this is encoder, and this is decoder. To describe positional information in input sequence, absolute position embedding represents each absolute position L in a sequence with a unique position vector PL, and then adds a PL to the input embedding as the input to transformer model, as shown here. This input sequence, this position information. After embedding, we get the embedded input and the embedded positions, and then we put them together as the input to the transformer. One of the popular choices is a sinusoidal function, which is defined as here. This is a 2D distribution. Relative position embedding describes the relative positions of a query Qi to the element in the distribution key as shown here. Therefore, RPE can work on attention matrix with a summation before softmax normalization, as shown here. This is softmax. A token at position I is represented by using HI and PIJ, which are its content and relative position with the token at position J. The attention score AIJ between tokens I and J can be decomposed as 4 terms. There's a content to content, there's a content to position, and this is position to content, and this is position to position. Namely, the attention score for token pair IJ is computed as a sum of the 4 attention scores using these tangled matrices. QC, KC, and VC are content vectors. WQC, WKC, and WVC are embedding matrices. P is a relative position embedding vector. QR and KR are relative position vectors. Delta IJ is a relative distance between I and J, and the attention score AIJ tilde and attention output H out are computed by using these 2 equations. To incorporate positional information into attention score to describe relative position of 2 tokens XM and XN, the inner product is formulated by a function G that takes as input the token embedding XM and XN and their relative position M minus N, defined as here. The goal is to find an encoding approach for FQ and FK with the relative position of 2 tokens at positions M and N. Skipping the detailed derivation, the position encoded FQ is computed by using this equation, where theta is a preset non-zero constant. To generate a position encoded query and key distributions, the token embedding vector is rotated by M times theta, as shown here. This is input sequence, this is embedded Q or key distributions. This is the position information. By using rotation operation, we get the position encoded query or key as shown here. For more details, please check with these references. Thank you. Bye.